Welcome to the session 4 of real analysis. In the previous sessions, we have discussed what are finite sets and infinite sets, and we had studied some of the properties of finite sets as well. In today's session, we will be discussing what are countable or denumerable sets. A set S is said to be denumerable if there exists a bijection from the set of all natural numbers to the set S. A set S is said to be countable if it is either finite or denumerable. So, we have seen in the previous session that a finite set has got a bijection from a subset Nn of n onto the set S. So, a set is said to be countable if it is either finite or a denumerable set, that means there exists a bijection either from Nn onto S or a bijection from n onto S. And a set is said to be uncountable if it is not countable. Some examples of countable sets are the set of all even natural numbers, the set of all integers, the set n cross n, where set n is the set of all natural numbers. So, we shall see how they are countable. So, at first we will discuss how the set of all even natural numbers, say E, is countable. So, the set of all even natural numbers starts with the number 2, 4, 6, 8 and so on. Now, we have seen in the definition of countable sets that in order to a set be countable, we need a bijection from the set of all natural numbers to the set S. So, here the set S is same as the set E. So, we are going to define a bijection from the set of all natural numbers n onto the set E, which is the set of all even natural numbers. So, natural numbers 1, 2, 3 etc. onto the even natural numbers 2, 4, 6 etc. So, we can define a bijection by f is equal to f of n is equal to twice n, so that 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6 and so on. So, for each element in n there is a unique image in E, and for every element of E there is a unique pre-image in n as well. So, it is a bijection. So, thus we have established a bijection from the set of all natural numbers to the set of all even natural numbers, and hence E becomes a countable set. The next example that we had discussed is the set of all integers Z. So, Z, the set of all integers, is given by etc. -2, -1, 0, 1, 2 and so on. So, this set is the set of all integers, as we all know. So, in order to establish a bijection from n onto Z, and since Z has got a positive part as well as a negative part, whereas the set of all natural numbers has got only positive part and greater than 0, what we do is a classification of n into 2, namely the best classification of n is even and odd natural numbers. So, what we are going to do is we are going to map all the even natural numbers to the positive side or the non-negative part of integers, and all the odd natural numbers to the negative side of the integers. So, we have 1, 2, 3, 4 and so on, and here you have 0 on the middle, 1, 2 etc. on top, -1, -2 etc. So, all the odd natural numbers will be mapped to the negatives and even natural numbers will be mapped to the positive sides. And such a mapping can be defined also. F of n is equal to say 2n minus 2 for whenever n is even, and is equal to a similar definition for odd natural numbers will give you a precise definition of 1 to -1, 3 to -2 and so on. We can see such a mapping, and this is again a bijection we can see. The last one or last example is what is called n cross n, which is the Cartesian product of natural numbers with itself. So, a typical example of an element of n cross n is say 1, 2 or say 5, 6. These are examples of elements of n cross n. So, we are going to show that n cross n is a countable set. So, first we shall define or we shall enumerate all the elements of n cross n in an array form. N cross n, all the elements we are going to list out in an array form, say 1 1 on top, then you have 1 2, 1 3 and so on. Then we have 2 1, 2 2, 2 3 and so on. All these elements will be listed in an array format. Then we are going to arrange all the elements in a diagonal form, starting with 1 1, then taking 1 2 and 2 1 as the second diagonal. The third diagonal being 1 3, 2 2, 3 1 and so on. Like a diagonal pattern, we are going to arrange all the elements. So, what we are doing is we are going to arrange the numbers in this order: 1 1, 1 2, then we have 2 1, because 1 2, after that we have 2 1, then we have 1 3, 2 2, 3 1 and so on. So, we are going to arrange them 1 1, 1 2, 2 1, 1 3, 2 2, 3 1 and so on. So that an ordered pair Mn is arranged in an increasing order of, comes in the increasing order of m plus n as well as m. Because we can see, if you have ordered pair 1 2, we have the position of ordered pair 1 2 in the second diagonal before the number 2 1. So, the number 2 1 comes next to number 1 2. So, Mn appears in the increasing order of m plus n as well as the first element m. Now, having a position function for Mn, ordered pair Mn, how we can define a position function, say h, for this ordered pair Mn, or we are going to define a position function from n cross n onto the set of all natural numbers n, so that we can say that the ordered pair Mn is in the first, second or third or whatever position it be. So, in order to define such a function h from n cross n onto n, first we can see in this arrangement, suppose we are going to find the kth diagonal, how many elements are there in the kth diagonal. So, how we can get onto the kth diagonal, that we are going to see. So, suppose we are defining a position function, say psi of k, it is equal to, we can see the first diagonal is having a single element 1 1, the second diagonal is having how many elements? 2 elements, namely 1 2 and 2 1. This is the first diagonal, this is the second diagonal, then third diagonal contains 3 elements, namely 1 3, 2 2 and 3 1. So, this is the third diagonal. So, in general the kth diagonal contains k elements 1 k, 2 k minus 1 and so on up to k 1. So, the number of elements in the kth diagonal or up to the kth diagonal element is given by psi of k is equal to 1 plus 2 plus 3 plus etc. up to the number k. This denotes the number of elements up to the kth diagonal. And we have seen in a previous example or previous session, by mathematical induction, principle of mathematical induction, the sum to the first k terms of a natural numbers is given by k into k plus 1 by 2. So, with the help of this function psi, we are going to define the function h from n cross n on to n, which is known as a position function. It is defined as h of m comma n is nothing but psi of m plus n minus 1 plus m. Psi of m plus n minus 1 plus m, because we can see from the arrangement of numbers an ordered pair mn appears in the m plus n minus 1th diagonal. Say for example, ordered pair 1 1, so m plus n is 2. So, m plus n is 2 and so it appears in the first diagonal. The next ordered pair is 2 1 and 1 2, both add together to get 3, but that appears in the second diagonal. The third diagonal element includes elements of the form mn, where m plus n is equal to 4 and so on. So, we can see that an ordered pair mn appears in the m plus n minus 1th diagonal, and so we have up to m plus n minus 1 means you are having m plus n minus 2, it is not 1, that is a 2 over there. Psi of m plus n minus 2 plus m. Now, this function h of mn is equal to psi of m plus n minus 2 plus m is a bijection from n cross n onto n. And because it is a bijection, it can be considered as a bijection from n onto n cross n itself, that does not matter. So, this shows that n cross n is a denumerable set and hence it is countable. We shall see another theorem which states, suppose S and T are sets and T is a subset of S. If S is a countable set, then T is definitely countable, that means subset of a countable set is definitely countable. And if T is an uncountable set, then S is an uncountable set. We have seen a theorem, similar theorem in the case of finite sets, it is a countable counterpart of that. So, if S is countable set, then T is definitely countable, and if T is an uncountable set, then S is an uncountable set. So, this is actually the it is like P implies Q and negation Q implies negation P. So, we need to prove only one statement, and this proof it's quite evident because it is a countable set means it is either finite or denumerable. The finite part we have already seen. Now, if S is a countable set, then definitely any subset of the countable set is also countable. So, the proof is quite simple. Another statement is, or another theorem states that the following statements are equivalent, namely, if we have a set countable, definitely there exists a surjection of n onto S, and if there exists such a surjection of n onto S, definitely it becomes an injection, and if there is an injection of S into n, then that set is countable. So, we need not establish a bijection as always we have defined in the case of countable sets. A bijection is not required for a set to be countable. A surjection or an injection is required so that the set is countable. That is the meaning of this theorem. So, a set is countable implies there exists a surjection of n onto S. That is quite evident because a set is countable means it has a bijection, and a bijection means it is definitely a surjection. If there exists a surjection, we can create an injection from that onto n, S into n, we can create an injection by taking the least of all the pre-images. We can take the injection of S into n, and if there is such an injection, definitely it becomes a countable set. So, that is this theorem. Now, we are moving on to an important result in real analysis. The set Q of all rationals is countable. So, before going to the proof, we would see what a rational number means. So, a number of the form P by Q, where P and Q are integers, is called a rational number. So, now we are going to see that the set Q of all rational numbers is countable. So, before going to the proof, let us look at the definition of Q once more. It is a number of the form P by Q, where P and Q are integers, means both P and Q can be positive or both can be negative, or P can be positive and Q can be negative. So, there are three options. If both are positive, P by Q is positive. If both are negative also, P by Q is positive, and if P or Q is negative, then P by Q becomes negative. So, keeping that in mind, we can divide or we can classify this Q as Q plus union set 0 union Q minus, where Q plus is the set of all positive rationals only. We are taking into consideration all the rationals of the form P by Q, where both P and Q are of the same sign. Then set 0 and Q minus means P and Q are of opposite signs. Now, considering our Q plus, an element of Q plus is of the form m by n, where both m and n are natural numbers. Why? Because natural numbers are positive integers. So, we have Q plus consisting of all the elements of the form m by n, where m and n are elements of n. Therefore, we can define a bijection, say f from n cross n onto the set Q, namely f of m comma n is equal to the ratio m by n. Now, this is exactly a 1 and on2 function, because for every rational number Q plus actually. For every rational number in Q plus, we have an m and n in n cross n, such that f of m comma n is equal to m by n, and the converse also. So, this f becomes a bijection, and since we have already proved that n cross n is countable, we have proved that there is a bijection from n cross n onto Q plus, and therefore, Q plus 1 is also countable. A similar argument can show that Q minus is countable, and so if Q plus is countable, Q minus is countable, and set 0 is countable, we can show that it is a countable set. Q is a countable set. So, we have to prove that a countable union of countable sets is countable. That is what we are going to see next. So, we can see in the next result, if AM is a countable set for each m element of n, then the union of this AM is also countable, or in other words, in a more simpler language, we can define or we can restate this theorem as a countable union of countable sets is countable. Now, how this is possible? We can see that is the underlying result for showing that Q is countable here, because Q plus set 0 and Q minus are all countable sets and hence the union becomes countable. So, we are going to prove that result. Suppose we have A1 is equal to the set of all elements of the form A11, A12, etc., A1n, etc. A2 consists of all the elements of the form A21, A22, A23, etc., and so on, as we have defined or arranged the elements in the case of n cross n. We can arrange all these elements in the format A11, then A12, then A21, A13, A22, A31, and so on, and we can define a similar function as we have defined in the case of H. From n cross n to n, we can define a similar function and show that this is also a countable set, and that is the proof of countable union of countable sets is countable. Okay. Then we have a next important result, which is known as the Cantor's theorem. The Cantor's theorem is a very important result in real analysis, which states that if A is any set, then there is no surjection of A onto the power set of A, that is P of A, of all the subsets of the set A. So, in a previous session we had already discussed the power set of A contains 2 power n elements. Now, in this Cantor's theorem, we are going to show that there exists no surjection from A onto the power set of A. So, in order to show that there is no such a function existing, in mathematics what we usually do is, if possible, let us assume that such a surjection exists, then we will arrive at a contradiction. So, that is known as the contrapositive method that we will be doing. So, we are going to assume that if possible, let phi be a surjection from A onto P of A. So, what we are going to prove is, we are going to show that if A is any set, there is no surjection of A onto the power set of A. So, if possible, we have taken a surjection, say phi from A onto P of A is a surjection. So, surjection means what? For every subset in this set, we have a pre-image. So, we have yes. So, we have for any element A element of capital A, phi of A is definitely an element in P of A. Why? Because phi we have defined to be a surjection from A onto P of A, and so for A belonging to A, phi of A is an element of P of A, which implies that phi of A is a subset. Is a subset of the set A. So, subset of the set A means we have a Venn diagram something like this. We have the set A here, we have a subset of A, and A is an element of A. So, it can be either inside the subset or outside the subset. So, phi of A can either belong to inside of this, A can either belong to phi of A or A cannot belong to phi of A. So, there arises two cases. So, we are going to define a new set, say D is equal to the set of all elements in the set A such that A does not belong to phi of A. So, that means we have taken phi of A to be a subset of A, and as we discussed here, an element of A can be either belonging to the subset or it can be outside the subset. So, we are going to define D as the set of all elements in the set A for which A does not belong to phi of A. Then consider, consider this surjection, this definition of surjection that we have. So, D is definitely a subset of A. Why? Because by the definition of D itself, D is a subset of A, which implies D is an element of the power set of A. So, D belongs to the power set of A, and phi by our assumption is a surjection. So, for every element of P of A there exists a unique image, pre-image. So, this indicates that there exists some A naught belonging to A such that phi of A naught is nothing but D. Because why? Because phi is a surjection. Because phi by our assumption was a surjection, and so phi of A naught is equal to D. Now, two cases arises. Case 1, what are the two cases? This A naught may belong to the set D, because A naught is from A, D is a subset of A. So, this A naught can belong to D or A naught cannot belong to D. So, if A naught belongs to D, what was the definition of D? D was the set of all elements in A for which A does not belong to phi of A. So, we have taken the case A naught belongs to D, and what was D? D is actually phi of A naught. Therefore, what we have is A naught belongs to phi of A naught, but by the definition of D, can A naught be an element of D then? No, because D consists of all the elements of A for which A is not belonging to phi of A, but we have here A naught belongs to phi of A naught. So, that means we arrive at a contradiction. So, this implies A naught does not belong to D. Okay. Now, case 2 is exactly the same. Let us assume that A naught does not belong to D, but then A naught is not an element of phi of A naught, but then by the definition of D, A naught belongs to D. So, again we arrive at a contradiction. So, why this contradiction arises in both the cases? Because we cannot establish such a surjection from A onto P of A. This is what is the proof of Cantor's theorem, and this is following the Russell's paradox in set theory. So, this proof shows that we cannot establish a surjection from any set onto its power set. In today's session, we have discussed some of the properties of countable sets and a very important theorem in real analysis, which is called the Cantor's theorem, which states that there is no surjection from a set A onto the power set of A. So, with this we can conclude what are countable sets and what are the properties of countable sets. Thank you.